Good morning and welcome to another Micrographics webinar. I'm your host, Carl van Rooyen, application engineer with Micrographics. Today's webinar on the manufacturing side is looking at how to accelerate time to market through the use of Autodesk digital prototypes. On our agenda for today, we will have an introduction going through what we are going to be covering and the idea behind digital prototypes. We'll be talking a bit more about actual digital prototypes and design automation within the digital prototype. The design automation will break down into some basic functionality inside of Inventor, looking at the design generators or design accelerators built within Inventor, our logic, being able to create rules using our logic, and the use of Inventor's API. We'll then move on to data management, having a look at Vault, both basic and professional, just a very high level overview. And then what we can do with our digital prototype is simulation. So we'll have a very quick look at the simulation side of things before we then close off with a summary and Q&A. And the running theme throughout this webinar will be how the digital prototype can tie into your overall system within the company, starting off with the design, the digital prototype, how to manage it, how to simulate that, and then later on how that could move through to an ERP system. So we'll move on to the introduction. And we start off here basically looking at how rapid technological advancements intensify global competition, and shifting consumer demands are significant market forces that are affecting businesses today. So we've got these three big forces that are potentially affecting your business and affecting how you operate and how quickly you need to turn around product designs. And companies need to be able to adapt quickly to these changes to remain competitive and to be able to meet customer expectations. And we'll see a big shift from the consumer demands and customization in the fact that everybody wants something custom. They want it customized to their likings. So it's no longer choose a color as long as it's black, like Ford used to be with their Model Ts. It's now every single car coming off the production line is a custom car, if we're looking at automotive manufacturing. But other products are similar. We're looking at that demand in customization. Just some facts here. Researchers indicate that 45% of products are delayed by at least 1 month. So that means others could be delayed by longer. And 50% of projects experience scope creep, meaning that the project ends up being much bigger than expected. These metrics highlight the challenges companies face in maintaining timelines amidst growing complexities. So as they need to customize things, project creep could change. Projects get delayed, and that impacts. So failing to address these challenges can lead to unpredictable costs. So project creep, project grows, costs grow. Delays, you might have to pay penalties because of delays. So there's unpredictable costs that may negatively impact overall financial stability and planning for the company as a whole. Failing to act can result in lost opportunities, which directly affect revenue generation and market presence. Essentially, if you can't quote quick enough, if you can't customize a model and get a quote to the customer quick enough, they may go somewhere else who could quote them quicker and have a shorter timeline. And so competitors, where you can lose out to competitors who adapt quickly, they can pose a higher risk, potentially overtaking market share and profitability. So we're seeing the shift over to more customization. And if you're from a design process can customize models quicker and easier, you can shift into this area where you can provide that quicker to the customers, that information quicker to the customers. But we still need to keep down those unpredictable costs. So we'll be having a look at how we can do that. And we see a lot of times as well that most companies operate in what we would term functional silos. Every department head sets up their own processes using whatever tools are available. Sometimes it might just be Excel and email, and little attention is paid to how information flows across the enterprise. Each person does their own thing and just sends information wherever they need. So while individuals may be organized, processes that involve people and information from multiple functions within the business could be chaotic and inconsistent. Product information that starts at the design process is the lifeblood of manufacturers. It could be hard to find, it could be inconsistent, and often outdated and difficult to interpret. So that digital prototype, the information housed within that digital prototype, might not be easily accessible to everyone. There may not be channels that are available for people to get the most up-to-date information. And this can lead to errors, delays, inefficiencies, and perhaps more importantly, low morale. And that can lead to difficulty in hiring and retaining the best people. Most companies aren't even aware of the layers of redundancy and slack they've built into their business as usual process. Now, I often hear, we've always done it that way and it works, so why change it? And this is what I mean by that business as usual. This chaotic, we've always just exported that file and emailed it to this person and then they handle it and do what they need to do with it. And, we often hear that, it just works that way, why do we need to change it? But we need to start looking at how can we optimize processes. So I like this image here. There's a lot of chaos going on here, a lot of PDFs floating around, a lot of Excel documents, emails back and forth. And this process is something that can be neatened up, starting with the digital prototype. I think that is where everything starts in a company that produces product, that manufactures product. They need to know what's in the product, how it's made. So talking about that, how do Autodesk digital prototypes help clean up this process? That is the starting point. So if we pay more attention to that foundation, we can help to streamline the rest of the process through the company. And that starts off with design automation. The idea here is that you can automate the creation and documentation of accurate, viable design alternatives, so that customization, we've got design alternatives based on customer specification and market needs. So we can build into your product automation that helps the customization process. An example I always use is making a conveyor belt longer. If you go over a certain length, you need more supports under the conveyor belt. What we'll look at from an automation perspective is how do we have those extra legs added in? Are there certain rules about how they can be added in? And that comes all the way from the beginning with the start of the design, building into the design, the automation process, and that allows for quick and easy reuse of that design for subsequent customers or subsequent specifications and changes that need to be made. Then we move on to integrated processes. This is where the data management comes in, and integrated processes allow for enabling changes to be tracked and incorporated faster. That's just one side of it. Looking at data management, that we'll go into a bit deeper, but we're looking at access to information, roles and responsibilities, who can edit what, the biggest thing, tracking change, and reusing data, taking an existing design, duplicating it, modifying it for the customer's needs. And then the third process, minimizing physical prototypes. Digitally prototyping and validating more of the design before production is going to save costs on the physical prototypes and time to produce and test physical prototypes. often testing will be destructive. So there's a lot of material, man hours that goes into physical testing for something small to be an issue that has to have a whole new product remanufactured with that change. Those small issues could be identified ahead of time by simulating the prototype and the digital prototype and seeing how it behaves. So these are the areas that we'll be concentrating on, mainly within this webinar. And let's have a look there how this can also help streamline. So the digital prototype is just the starting point, as I've mentioned. It feeds into the rest of the business systems that support the manufacture of the product. Bringing a product to market isn't just about great design. We're not just looking at the design side of it and creating that great design. The digital prototype, it's about speed and efficiency. We have to be able to do it fast. We have to be able to do it accurately and efficiently. But too often, delays, miscommunication, and bottlenecks slow things down. There might not be clear communication with the customer. There may be delays in changing the size of something because the design fails in ways that weren't expected. Physically, not physically, let's say, the features within Inventor could fail and not be able to calculate because of unforeseen changes that are not covered by, let's say, the design automation. And that's where the right digital tools will make all the difference. By being able to streamline collaboration and improving coordination between teams, companies can work faster, iterate more effectively, and keep production moving. And what is the result? We end up with shorter development cycles due to the automation. This provides fewer roadblocks, that automation providing fewer roadblocks, and then the ability to respond to market demand faster than ever. So when teams stay connected, the innovation doesn't just happen, it also happens faster. So for this webinar, as I mentioned, we'll be concentrating on the first 3 steps in the life of a digital prototype. These are the design automation side of things, where we will be building in ways to quickly change design to meet customer specifications. So take our design, put in some automation processes into the design to be able to customize it. Data management, basically how to find and reuse data as well as manage change. There are various other sides to data management as well. And then product simulation, using the digital prototype to drive down the cost of physical prototypes and validate customized products. This will lay down the foundation for the rest of the data-driven ecosystem that can help drive down the overall time to market. So let's jump straight in with design automation. Design automation allows to streamline workflows by eliminating repetitive manual tasks, such as parameter adjustments, component placement, or configuration updates. With predefined rules and templates, designers can quickly generate multiple variations of a product without starting from scratch each time. Essentially, they can create a duplicate of the product, enter in a few new values to have the product update. This speeds up the design cycle, allowing companies to bring products to market much faster while freeing up engineers to focus on innovation rather than routine tasks. They don't want to be manually every day changing the same parameters to make a fence longer or shorter, or to make a conveyor belt longer or shorter or wider. Wouldn't be able to automate these tasks. The issue with manual design processes are that they are prone to human error. That can lead to costly revisions and delays. Often that's only picked up during manufacture. Hey, these 2 plates don't line up, or hey, the conveyor belt sagging under the weight of the product that is on it. So design automation ensures consistency by applying predefined constraints and logic. Essentially, I'm going to use the conveyor belt as an example again. If we make a conveyor belt too long, it needs to have supports under it. So we can have consistency in logic that says, okay, if the conveyor belt is over a certain length, ensure that there is a minimum or maximum distance between the legs. So every 1 meter, there needs to be another support under the conveyor belt. So that frees up the designer to not have to think about it and go, oh, what was our design rule? Did we have to do it every 800 or every 1.5? The built-in automation puts that support in where it needs to be. So this can significantly reduce mistakes. Automated validation and rule-based checks also help catch issues early in the process. So you can have checks and balances where rules look at what the user inputs and says, okay, this is inside or outside of the bounds of the design, and adjust accordingly. So this can avoid late-stage modifications that may only be caught in manufacturing and accelerate the approval process. This results in fewer design iterations and a more efficient workflow, and also faster time to market. So you're going to hear me saying that a lot. Get to the market faster, be able to quote faster, get your product to the client faster. So design automation has various levels to it. The first level of design automation I'm going to look at are the design accelerators / generators. These are built into Inventor. They are pretty much out the box when you install Inventor. And most of what I'm going to be discussing today is going to hinge around the use of Inventor. It is the hero product from Autodesk for mechanical design, and also Vault from a data management perspective. So in the assembly environment in Inventor, we have these design accelerators. They basically allow you to quickly generate geometry by inputting information rather than having to sit and draw things. So the first page I have here is just an overall view of the different types of accelerators we've got. Some of these accelerators or generators also have submenus. We see spur gear there. We can do bevel gear, various types of gears, or even V-belts, synchronous belts, chains. So there are various generators. There's a list up on the screen that can be used to generate geometry, but they can also be used as calculators as well. You can calculate power transmission. There's a lot of like spline calculations, V-belt calculations to ensure that what you're putting into the design is not going to fail. So there's also a bit of the double checking and validation built into this as well. So I'm going to highlight a couple of these in the next few slides. Here, just on the right-hand side, some of the engineering calculators. So you can see drum brake, bearing, separated hub, power screws, and so on. So those calculators I mentioned as well. And a lot of the individual generators will also have calculators built into them as well. So if you're putting a key on a shaft, there's a calculator to ensure that that key is big enough and strong enough for the power transmission through that shaft. The first accelerator that I'd like to highlight is the frame generator. The frame generator allows you to use a reference component. In the picture on the right, it's the big transparent box. This allows you to have a reference to where you want to place your structural frame members. Most often this is used for your standard steel cross sections, square tube, rectangular tube, I-beams, channels, angles, etc. And this reference part can be used to place down those steel frame members. It allows you to quickly add these selected profile sections. You can choose the standard, the cross section, the size, material, appearance, and even position of these objects. You can reuse as needed as well across, so you can take a single frame member and use it in multiple locations. And it's also easy to add end treatments, things like your miters, your overlaps between the ends of the tubes. You can choose how they terminate against each other. And it's also easy to update. So if you change the reference model, then the frame updates automatically. So later on, when we look at our logic, we could use our logic to drive the shape of that reference frame, reference design, and then the frame will update automatically. So that is our first generator that we'd look at. Second one is, as I mentioned, the key connection generator. In this case here, we're looking at speeding up that tedious design task of having to model in the keyway and then also modeling the key and placing and constraining the key. In the case of the key generator, it allows you to easily create key and groove geometry. In the dialog box, you'll see bottom right-hand corner, select objects to generate. So you can do the key, the groove in the shaft, and the groove in the pulley or hub that is connected to the shaft. You've got those three options. You can pick and choose which ones you want. Also allows you to choose from existing standards. So right at the top there, you've got the drop-down menu, you've got the ISO 2491 key with its size. You can choose an existing standard key, so you know you can get that off the shelf from your local supplier. And it's placed using reference geometry. You may have work planes and sketches or edge geometry that you can pick to position the key on the shaft. There is also a loads calculator. So if we are wanting to ensure that the key is big enough, there is a calculation page that you can fill in your information with regards to the expected loading, the material used for the key, various information to go in here to then calculate whether or not that key is sufficient in size. Then the last one to cover is belts and chains. So once again, very similar to the key, we can create belt and chain geometry quite easily by selecting existing standards. So we'll see there's the synchronous belt standard that's been chosen. There is then various reference geometry to pick to place the belt. So your belt center line, your pulleys, you can use existing pulleys or just pick a center line to place a generated pulley and it will generate the pulley geometry for you. And once again, it can also be used as a calculator to calculate the power transfer through the belt. So you can create some more complex systems with this, multiple pulleys, and it creates all the geometry for you quickly and easily. And using these design accelerators helps you once again to create that digital prototype faster, but also allowing for quicker updates when needing to change the design. So if we need to transfer more power through this pulley, we can easily go into the belt generator. It's a feature within the browser that can be edited and adjusted as needed. So we can adjust the belt width, have the belt geometry and the pulley geometry update to allow it to transfer more power. So part of the design acceleration process is being able to make those changes quicker. So with that being said, we're going to move on and have a look at our logic, because our logic may drive the more overall designs and the bigger scheme of things. And these smaller design accelerators are the easy low-hanging fruit that you can use to adjust designs quick. So looking at our logic, I have spoken about rules that would control certain aspects of a design. But what are rules? Rules, we look at rule-driven automation. Rules are built into the model. It's a piece of code written in our logic or straight VBA script. So it is programming that is built into the model, and it is used to drive the design intent. The example to the right-hand side here is machine guarding to protect users or operators from the machine. And the design intent for the machine guarding may be that, you've got a standard span of wire fencing. Maybe it's a 2.4 meter standard width. So if the machine guarding is longer than 2.4 meters, the design intent means that we need to add in an extra post. We're going to have multiple panels for that. So we can create these rules that allow us to handle customization. If the user says, I need a 6-meter long piece of fencing, the design automation can pick up that, okay, that's more than the 2.4 meter standard size. Let's put in 2 standard size fences with the posts in between, and then put in a filler piece that is shorter with a post at the end. And the rule can handle the placement and inclusion of those extra components. So all the user has to worry about is, how big is the area that I need this fence to cover? It's 6 meters by 3 meters, and the rules customize the model according to that input. So this way you have standard rules that run every time that the machine guard is customized, and you have a standard model that is output. The filler piece is always in the same corner, it's always in the same spot, and you have that consistency driven into the design. So it allows for the handling of customization. It allows for the user to easily adjust parameters for the customer's needs, and this rule then adjusts all the parameters that are required to meet the customer's needs. A big part of this automation is also to catch errors. If the user says that they want the fence to be 3 meters tall, but your standard height is only 2 meters, you can catch that error and say, sorry, that's over the standard height. You need to reduce the height or create a custom extension. So we can actually catch errors in the design where values go outside of the design intent. The iLogic coding is also supported by forms. So forms are also built into the model. They form part of the iLogic. These allow the users a user interface. So the designer has a user interface that we term a form that they can use to input information for the design. These forms are easy to set up. Like I said, they're built into the model, and they can be customized to your design requirements. So this form here relates back to the machine guarding, and I quite like this form because they have various tick boxes to basically include or exclude posts for that machine guarding. So as a total, there is the availability of having, or you're able to have a total of 8 posts with panels fencing in between each post. So the top section there, allowing the user to choose how many posts they require. Then they can choose from the panel length, they can set the size of each of the panels, and the naming referring down to the image. We can see that Y1_2, we can enter in that length there. So length 1 for 1_2 for basically X and Y. We can then set a size. And so all of this input that the user will fill in on the form is handed off to the rules, and the rules will then run and update the design accordingly. We will see this in action in a video coming up soon. So the forms allow for user input. It allows for the design to be customized within a specific limit. So we are able to simplify the design choices and limit the user's input on the design. So we can stay within the design limitations or manufacturing limitations. Then a step up from iLogic is going into custom applications using Autodesk's API. So the API is Application Programming Interface. It is a language that is written so that you can tap into, in this case, Inventor's functionality to be able to create programs that will drive automation. So this allows users to create their own apps or reach out to developers to create apps for them. And as Micrographics, this is what we have done for customers over the years. We also have apps that we group under tools for Inventor that run and do certain tasks that may be repetitive, and it automates the process. So the API allows you to link your app into your Autodesk products like Inventor and Vault, AutoCAD, and create more robust standalone applications or add-ins that allow for automation of specific repetitive tasks. So as an example, we have a couple of applications from DXF Exporter, which will export DXFs of all of the sheet metal components in a design. So you can take your assembly, open up the app, say scan for all my flat patterns, and export out the DXFs for all the flat patterns. We have another one called Duct Pro, which allows you to choose from a user interface the style of duct connector or type of duct, if it's a reducer, if it's a Y, if it's a lobster back bend. Set the geometry and the dimensions for that, and it will generate the predefined model to your sizing and put it into your assembly. So those sorts of automations allow for quick and easy creation of geometry or creation of deliverables. Tab and slot is actually an add-in. This icon here in the center, tab and slot, it's an add-in that lives inside Inventor, and you pick geometry on your model and it will generate tabs and slots on your sheet metal components. And that is another level of design automation that can be achieved through programming of add-ins and apps. So it's time for a quick demo. I'm just going to pause this here. Now that we've spoken about automation and we've seen how it could potentially speed up design and reduce errors, we're going to now have a look at this video, which also includes structured data. In other words, there are specific assemblies within this design that have been automated. They've got that iLogic built into them. The information is structured in such a way that it is easy to reuse. So we'll see that how this well-organized data set allows for quick design adjustment without a lot of manual rework. And instead of modifying each component individually, changes happen dynamically, keeping everything aligned with predefined rules. This not only saves time, but it also ensures consistency across the design. So if we're reusing a conveyor belt and changing dimensions, we have consistency within how that conveyor belt is manufactured. Another key benefit is the standardization. So we're working with a structured framework. Teams can enforce best practices within this to reduce errors and simplify collaboration. Whether you're going to be tweaking dimensions, materials, or configurations, everything updates seamlessly, helping engineers focus on innovation rather than repetitive tasks. Ultimately, this data-driven approach streamlines your workflows, making design faster, smarter, and more reliable. So as you watch this, just think about how structured data can help optimize your own design process. Think about designs that you work on and how you could apply the structured approach to it. I'll also voice over this as it plays just to explain what is going on. So in this case here, we have the machine guard. The user is going to open up that specific assembly. At the moment, it only has a single fence, but they have a form that they can launch. This form will look familiar. And they pick and choose from this form what they want to include in the model. And it is immediately updated on screen. Very quick and easy to generate that assembly. What they're now looking at is Vault. We'll talk a bit about Vault later on. They're seeing where is this design being used, what information is it linked to, and they're going to do a copy design, essentially duplicating that conveyor belt to create a new, longer conveyor belt, but of the same design. So they're going through the process now, reusing existing portions and copying the portions that need to be customized. Notice they haven't even left Inventor. They're using Vault add-in directly inside of Inventor to be able to make these changes, create the copy design, search for it, and now placing it using armates. So there's an armate built into the design to easily connect the conveyor belt ends together, reducing the need to use constraints. And now within the conveyor belt, they're using a form once again with our logic to update the length of that conveyor belt. So in this case here, they're going to take that value across and they're going to update or create a pattern. Now they notice the fence is not big enough, so they'll come in and adjust the length of the fence. They're going to add an extra 200 millimeters and the design updates. All through our logic for the model changes within the design. Vault copy design to duplicate the original conveyor, to shorten it and place it outside of the platform. So they very quickly, pretty much in real time here, seeing how we can quickly make changes to the machine guarding to make space for more conveyors, also duplicating and placing those conveyors. And this brings us nicely into Vault. So Vault is your product, or basically your data management that would be used along with your Autodesk design products like AutoCAD, Inventor, various other products that are also able to tie into Vault. But we have a couple of different levels of Vault. You have Vault Basic, which is the entry-level data management platform. It's included with your licensing for Inventor Professional and AutoCAD, as well as your product design and manufacturing collection. So if you have one of those licenses, you have access to Vault Basic. Essentially, it is a platform that you would install on a local server that provides a secure location to store your CAD and other files. So the server would then require login from the users to be able to access it. So from their design computer, they would open up Vault. They have to sign in. So they need a username and password to access the data. Vault Basic goes a few steps further and allows for control over who is editing the file. So if the first user gets a file and they check it out, they are working with it, the file is unlocked for them. But then the other users, the file is locked and read-only, they cannot change it. So this adds a level of control over who is changing files at what time. You can also have user roles set up where certain users can only download and view files, where other users can edit files. And Vault Basic also brings in the first level of history management. It brings in versions. Every time a file is checked out, modified, and checked back in, a new version is created. Vault Basic also sees and understands file relationships. When you check an assembly into Vault, Vault tracks how the assembly is connected to all of the other components, and it knows the folder or the hierarchy of that assembly. So Vault will know what components are used within the assembly, but it also knows the reverse. If you pick a component, Vault can tell you where that component is used, which assemblies and drawings that component is used in. And this opens up a whole scope of area for Vault to be able to control and manage that data. If you go to rename files, you need to now change the part numbering scheme and you want to update the file names to match. Vault can repair the relationships between the assembly and the renamed part files. Normally, that link is broken. Vault or Inventor says, I can't find the related parts because the names are different. Vault automatically updates those relationships. This allows for very easy design reuse. We saw in the video, the user used copy design to take an existing conveyor belt, create a duplicate of that. Most of the components were duplicated and used separately to be able to change the length of the conveyor belt. And that copy design allows for renaming and then relinking of all of the components in the new assembly. And so we have this design reuse where we can do the copy design, and we can also have standard libraries, out-the-box libraries, or off-the-shelf libraries that can be used within Vault. So just looking at the copy design, we can take an entire design and copy it from folder A to B and rename all the files as needed. Then going up to Vault Professional, it's got all the Vault basic functionality and more. So it's a higher level of functionality within the software. From an automation perspective, Vault Professional has API that can be tapped into for those custom applications. But built into the software, we also now have life cycles. So life cycles allow for the status of a file to be shown. Is it currently work in progress? Is it for review? Has it been released to manufacture? And each of these life cycle states can control access to the file. So if it's in work in progress, manufacturing cannot access that file. Manufacturing users cannot see it or use it because it is still work in progress. If it's for review, the design is locked down until it is approved and released for manufacturing. Even when it's released, it will be locked for changes so that it cannot be changed while being manufactured. And if change is needed, then Vault has the ability to create and track engineering change orders. So here we can control and track changes that are being requested and that are being active within Vault. So that would allow a user to take part from an assembly or a design from released back to work in progress and track that change history, and also track changes in revision. We're now going into a revision A or a revision B of that file. Vault also has items. Essentially, items allow you to convert a design into an internal object that is linked to multiple files, but can also be exported out for ERP. So an item would be an object that shows you the CAD bill of materials, so the bill of materials pulled from the design from Inventor. You can then add items that are non-design items, things like paint, grease, cable ties, to create a more complete engineering bill of materials. The item is linked back to the data, so back to the CAD files. We can see which CAD files are linked to that item, but it can also be linked to documentation like specifications, instructions, various documentation that might need to go along with that design, spare parts lists, things like that. And items can allow you to integrate with ERP to be able to synchronize with the ERP system. You may have a life cycle on an item. When it gets released, that item gets pushed through to the ERP system so that the ERP system knows, okay, here's a new item, it's been released for manufacture. We now need to start gathering information for the ERP. Vault Professional also comes with the ability to have a Vault Office license. It is a license for managers to be able to access Vault and access the information that is stored within Vault. And also Vault Thin Client. This is free to use from a computer on the same network as the Vault server. You log into Vault using your web browser, and you can then view information within the Thin Client. Typically, this would be used for manufacturing to be able to log into Vault, search for a released drawing, and print their own copy of the drawing. They don't have to run to the design office, interrupt the designers, and ask them for a printed copy of a drawing. They can also download files from Vault as well. So those are your levels of your data management that can be used directly with Inventor, not going into any of the PLM or cloud solutions. And this brings us to product simulation. So once we have this digital prototype, we can then simulate so that we can catch any potential design issues up front. before doing any physical prototyping and testing. So we can do digital testing to simulate expected loads using the digital prototype. We can better predict the product behavior before we've even created a physical prototype. And we can refine this digital model so that, so we can refine the digital prototype, not the physical. So we can go through various iterations of the digital prototype, and therefore we reduce the need for a high number of physical prototypes. In turn, this is going to reduce the cost of physical testing, which is, once again, often destructive. And particularly here, talking about Nastran being one of the options to do stress testing, both linear and non-linear testing, buckling, apologies. So there's various options available within Nastran from a simulation perspective. And once again, Nastran is included with the product design and manufacturing collection. So just a video here to show how this would work. Once again, we have a design that is set up. It may be something that is customizable, but it is set up here. It's a door that will open. We're looking at what's called a direct transient response. We're going to simulate the door opening, and we will see how the stresses in the part respond, or how the part responds stress-wise to this activity. So here's the door opening. It's going to lift 400 millimeters. We have time steps to show the acceleration or deceleration of the door, and the simulation is run. In this case, it's run over a certain period of time, so we get time steps, and you can view at different time steps what the stress looks like in the object. And we see quite a high stress, max 421. It was a little higher earlier, so this component might be an issue. This door has our logic built into it. Our logic just drives the thickness of the bracket that was in question. They're going to reanalyze the model, so nicely built in there is an option to rerun the analysis. The analysis runs, and we can see the new results. And now the bracket, definitely no longer the weakest point. We can see stress throughout the rest of the door, max of 250 there in the corner. And we can see that run in the animation. So you're able to quickly iterate on designs and rerun these simulations to get these results. You may have to customize according to the customer's requirements, and then simulate to make sure that the design is still within spec. Just a quick note from simulation. We do have other simulation products from Autodesk. Autodesk CFD is basically fluid dynamics. So we can simulate fluid flow, whether that is air, water, any basically object that is classed as a fluid. A couple of examples here would be airflow over objects for aerodynamics, wind loading, cooling of electronics. We can look at pressure drop in a system. So you can design, in this case, there's a valve there. You can tweak the design of the valve, the geometry of the valve, so that you can optimize the pressure drop through that system. And you can also look at moving parts, stirrers within a mixer, or valves, as the example on the right shows. We can actually have that valve opening and closing and see how it affects the fluid in the system. Then another one is the Autodesk Mold Flow suite of products. So taking your digital prototype, seeing how it's going to react in the manufacturing environment. So mold flow, like I said, there's various options, and within that suite, you can do compression or injection molding simulation. We can look at material flow analysis, and some of the products there also do design analysis. So your design engineers, as they are designing plastic components, those plastic components can be vetted for manufacturability within injection molding. So you'll be able to see certain areas are too thick or too thin, they don't meet good design practice. And that brings us round to our summary. As mentioned, looking at those first 3 stages of the digital prototype process and the whole lifespan of a design. So looking at the summary here, looking at the overall global climate, it is fast-paced, there's intense competition, and there's a big shift to customization. So you need to be able to customize quickly and get your product to market or get your product to the customer quickly. And digital prototypes helps us by allowing you to create a baseline product, a good data set with built-in design automation through either iLogic or API to update that design, customize the design, and validate the design to get it to the customer a lot quicker. And this brings in the connected product development process. The digital prototype is the start. It's the birthplace of the design and all the information required to manufacture that design. So we'd like to carry this data through the company's processes. As I mentioned, we looked at design automation, data management, product simulation, but this goes further to design collaboration. The more information you have in the prototype, the easier it is to collaborate and to convey information. We can then look at PLM workflows with the design, looking at the product lifecycle management, and then lastly, reaching sustainability goals. So a final thought here. We started off looking at a process that was potentially very unstructured, disconnected, lots of silos, and the digital prototype can be the start of creating a structured, connected, and accessible ecosystem that the design is easily updatable and configurable, even up to the point where it could be ported to a website where the customer directly customizes their product without an engineer needing to be there to change it. So that prototype from start to finish can help improve the overall structure of the data flow and process through a company. Okay, I'll pause there now at the end for any questions. I've been keeping an eye on the live chat. Nothing has come through on live chat. Let's give a minute or two, see if any information or any questions come through there on the live chat. I don't see anything coming through on the live chat. If you are watching the recording after the fact, please feel free to reach out, get in contact with myself. If you didn't catch my intro, my name is Carl van Rooyen, application engineer at Micrographics. My email is up on screen on the Q&A. And please feel free to reach out, contact me if you have any questions or basically anything regarding digital prototyping, Autodesk products. You're free to reach out and we will get back to you. Once again, thank you for your time watching this either live or the recording at a later stage. I hope you enjoyed it. Once again, this presentation was brought to you by Micrographics. If you haven't checked out our channel, please have a look at our channel, Micrographics on YouTube. Give it a like and subscribe. If you enjoyed this and you would like to see any more webinars, we have various application engineers that post up long format webinars. We host live webinars quite often, but we also do post up short tips and tricks type videos as well on our channel, both from a manufacturing as well as an architectural side of the Autodesk software. So Inventor, AutoCAD, Revit, various other packages as well. Once again, thank you for watching. Enjoy the rest of your